All right, it's review time. This was a pretty quick topic set. We were really just talking about momentum and how it relates to, say, the force. So in other words, you need to have a force in order to change the momentum of something. And then we looked at it as a conservation type piece. So in other words, we wanted to see how much momentum did we start with and how much would we end with. Okay, that was our two big concepts here. So let's talk about that first one again. An object gets in motion. Okay, so in other words, if you want an object's motion to change, okay, so if you want its velocity to change, we had to look at it in relation to, you have to apply a force. It goes back to what Newton was really talking about in his second law, F equals ma, but we then said, well, hey, what if we redid the A piece and actually talked about what A is, and A is nothing more than a change in your velocity over a change in your time, and then we just rewrite it a little bit, and this is the way that Newton really wanted to have it, was force is equal to a change in time, or force times a change in time is equal to a mass times a change in velocity, okay? And that's how we kind of wanted to talk about it. Of course, we know this as our impulse momentum, okay? So in other words, we're now back to, if you want an object to change its velocity, okay, we're going to change the amount of momentum that it has. And again, momentum is like that quantity of motion that we have, okay? So again, we look at our change in our momentum, okay? And then it's nothing more than apply a force for some given amount of time, okay? And if we wanted a change in momentum that would remain constant, we'd have to apply a force that we'd have to apply it for a longer period of time that would give us a different change in momentum, or we could look at it from the standpoint of, if we have a set amount of force, if we increase the time, then we can increase the amount of momentum change, okay? And so we looked at it from the standpoint of golf balls getting hit by golf clubs, as well as impacts from or a car impacting a wall, and then how it's changed as an airbag is deployed, okay? As an airbag does that, changes the amount of time, so it allows us to change the amount of force that we experience under that same momentum change. All right, so again, this was our formula, Ft equals mv, okay? And it is a change in that momentum, okay? V final minus V initial, okay? It's a change in the momentum, which really says it's a change in that velocity. In most situations that we dealt with with an object at rest, and then it's changing its momentum. But we do have the possibility of having it where the object is in motion, and then we change its momentum again, okay? So in other words, we see a baseball coming at us, and then we hit the baseball back the other direction. Okay, that's a big change in the momentum. Momentum, again, is a vector quantity. Okay, it is a vector quantity, so that it is dependent upon the direction. So if we have momentum going this way, okay, so momentum is going this way, and then we have momentum going this way, the two momentums are going opposite each other, which means that they would have opposite signs. Okay, so again, we're talking about it direction dependent. That was kind of the first thing that we like to do. Okay, we like to talk about momentum in terms of impulse, okay, because that's how you get it. Impulse causes changes in momentum. All right, the other thing that we looked at was the conservation of momentum. Okay, and so we looked at situations where the amount of momentum that we have in the beginning has to be equal to the amount of momentum that we have at the end. It's our basic conservation law, okay? And again, we looked at the momentum that we have before, okay, so we might deal with an initial velocity, and momentum that we have after, dealing with the final velocity. So again, it's looking at a change in momentum. This brought about a couple of different situations. Most of our situations with conservation of momentum, we started to look at things that we considered to be collisions. Okay, So we did our little carts, and we said the carts collide, and let's see how the momentum is conserved. We had two different types of collisions that could occur, and in all collisions, momentum is conserved. So this is good for all collisions. Okay? So all collisions conserve momentum. It's dependent upon whether the collision is elastic or inelastic, or whether energy is conserved. Because that was what we were talking about in last topic set. We were conserving energy. Now we're conserving momentum. If the collision itself is perfectly elastic, so in other words, if as the two objects come in contact with each other, even if they kind of seem like they squish together, as long as they spring back into the same shape, we consider that to be an elastic collision. Okay? So in other words, as long as the objects spring themselves back into the correct shape, we say it's an elastic collision, which means that momentum is conserved as well as energy. Okay, so the stored energy becomes energy that we get back. Okay, so in most situations, we look at the collision, we say, is it an elastic collision? Yes. Then momentum is conserved as well as energy. If we're looking at an inelastic collision, and now an inelastic collision is one in which the object itself gets kind of deformed, but it can't come back. So in other words, there was energy that was absorbed in the changing of the shape of the object. So like when a car starts to crumple, okay, there's a loss of energy because that energy has to crumple the car. And that's what we consider to be an inelastic collision. A lot of our inelastic collisions dealt with an object that was actually embedded into it or caught by it or stuck to it, okay? So the masses ended up adding together. Those are inelastic collisions, okay? And those, the energy is not conserved. There's always some kind of a loss of energy. And it could even be from the impact of sound, okay? Sound is another form of energy. So really we're studying two different scenarios, okay? Is it an elastic collision or is it an inelastic collision? And that should be kind of the one thing that you look at when you start to do these problems. Type of collision. So you need to say, is it elastic? Okay? Because if it is, we have momentum and energy both conserved. Okay? If it's inelastic, just momentum is conserved. Okay? Loss energy. We lose some energy along the way. Okay? So again, we look at those two situations. That's kind of what we're looking at. In fact, I've got that on the board. I'm looking over the board right now. It says all collisions, momentum, elastic collisions is the only one in which the energy is conserved. Okay, so that's our kind of big concepts of what we're looking at. So again, problem-wise, test itself. Okay, another one of those single-page tests. Some multiple-choice questions. So those are our concept questions. If you don't quite understand these concepts, go back, do the reading. Okay, remember there's always the websites that you can look at, and remember that you can always go back and watch the videos again. Problem-wise, I would expect to see something about impulse, so you're probably going to have to use the impulse. And you're probably going to have to do a conservation of energy problem, maybe one in which it's an elastic, and maybe one in which it's inelastic, and so you'll have to be able to determine which one is which. I don't know, if there's anything else, you should kind of go back over and look over the problem set and see if there's any questions there. But hopefully we got them all taken care of in class today so that you're ready for the test tomorrow. All right, good luck studying, and remember to get a good night's sleep.